In this video, we're going to talk a little bit about the limit comparison test for testing to see if a infinite series converges or diverges. So in the last video, we talked about the direct comparison test. And when we're trying to apply the direct comparison test, we can often determine what we think is the appropriate series to compare to, usually a p-series or a geometric series. But we run into a problem when we try to get the appropriate inequalities set up. So remember that to use the direct comparison test to show a series diverges, we need the terms of our underlying sequence to be greater than or equal to the terms from a known divergent test. Greater than divergent diverges. If we want to use the direct comparison test to show that a series converges, then we need the terms of our underlying sequence to be less than or equal to the terms from a known convergent series. Less than convergent converges. However, what can often happen is that we find a series that we want to compare to, but either the known series diverges and the terms we have are slightly less than its terms, less than a divergent is inconclusive, or the known series converges and the terms that we have are slightly greater than its terms, greater than a convergent, inconclusive. In these cases, we suspect our series is doing the same thing and behaving like the known series we found, but the inequalities go the wrong way, making the direct comparison test useless. However, don't despair. In these cases, the limit comparison test will usually work. So let's look at a couple examples where you can see the problem I'm talking about. So here's problem A. The sum from k equals 1 to infinity of 1 over k cubed plus 1. K cubed minus 1, excuse me. Well, the obvious thing to do is to sort of ignore the negative 1 or subtract 1 to the bottom and just say compare this to 1 over k cubed. Okay, or k to the negative 3, that's a convergent p-series. So we suspect that this thing is going to converge. However, when we start to use the direct series comparison test, we're out of luck because the terms of our series are actually are a little greater than the convergent p-series that we want to compare it to. Remember, making the denominator smaller makes the fraction a little bigger. So 1 over k cubed minus 1 is greater than 1 over k cubed. Having a series greater than a convergent series tells us nothing about the series you have, no conclusion. But we can use a limit comparison test instead. We'll work that one out here in just a minute. Similarly, on this one, if we have the sum from k equals 1 to infinity of k over k squared plus k plus 3, the k plus 3 is not as important as the k squared. The k squared dominates in the bottom, so you can sort of get rid of the k plus 3, replace it by just k squared, so we got k, replace the denominator by k squared, so you got k over k squared is 1 over k. Hey, that's the harmonic series, or a p-series with negative 1. That's going to diverge. So we suspect that this guy diverges as well. But once again, we run into problems with the directions of our inequalities. When we add k as a positive number, remember, so k plus 3 added to k squared is going to make the denominator even bigger, which makes the fraction smaller. So k over k squared plus k plus 3 is less than k over k squared, which is 1 over k. Oh, that's a bummer because it's in the wrong direction. So again, the direct comparison is of no use because showing that you have terms less than a divergent series really tells you nothing about the series you have. So we need to use the limit comparison test instead. And here's the actual test, and then I'll explain why it works. So if a sub k, first of all, the series that we're looking for is the sum from k equals 1 to infinity of a sub k. The known series is the sum from k equals 1 to infinity of b sub k. We know what it does. Just the same setup as we had before for the direct comparison test. So if AK and BK are both positive, so we're talking about positive term sequences, and then the series built on that, then if we take the limit as k goes to 0, no, k goes to infinity, I should say, excuse me. Let's fix that. That's not right either. Wrong symbol. Okay, there we go. So that limit there for is some limit L for some real number limit L. And the B sub k series, sum from k equals 1 to infinity of B sub k, also converges, then we know that the sum of the A sub k, our original series, must converge as well. So if it actually reaches a limit of the ratio of corresponding terms there, we put the one on the top is the one we are looking for. One on the bottom is the one that we know. And if that comes out to be a constant real number, hey, then this will converge. Of course, that'll be a positive number because both the AK and the BK are positives. Or it could possibly be 0, which is okay as well. If AK is greater than 0 and BK is greater than 0 again, and we have the limit as k goes to infinity here is a limit, L, or if that limit goes to infinity and BK diverges, then the sum of BK's diverge, then the sum of the AK diverges as well. So basically, if you get a limit, then if one converges, the other one does too. If one diverges, the other one does too. And in the case of the infinity limit, if you've got the A on the top, then that is going to be convergent, divergent as well. Now here's how the proof goes. So this is our hypothesis again, same thing we just said, that we've got positive terms, the limit exists. I've still got the same copy and paste problem. Let's fix that. Okay. All right. Then by the definition of a limit of a sequence, for every epsilon, well, specifically for the epsilon equal 1, there exists a m greater than 0 such that if k is greater than m, a sub k over b sub k, the thing we're taking the limit of, has to be less than that limit plus epsilon. And of course, it'll be really between that limit plus epsilon, that limit minus epsilon, but certainly we know it's positive. So in particular, we have it's between 0 and L plus 1. So that implies if we solve this inequality here by multiplying both sides by b sub k, which is a positive number, remember, we get AK is less than L plus 1 times BK right here. Well, let's call that sequence C sub k. So if the B sub k from k equals 1 sums to some number S, remember it converges, right? So that means it converges. Then what do we have? We have the sum from k equals 1 to infinity of A sub k is less than or equal to the sum of CK, because we do have the inequality going the right direction there. That's with our limit comparison test, basically. But that is 1 plus L times B sub k is C sub k. The 1 plus L is a constant, so we factor that out of the front of the sum, like that. The sum of the B sub k is that sum S. So this says that it does converge, and it converges to whatever this limit is, plus 1 times this sum, or less. Something there or less, for sure. So, and of course it's positive for some, for sure. So some positive number less than this here. So sum from k equals 1 to infinity of A sub k converges by the direct comparison test comparing to this sum of the C sub k's. We're going to do something similar for the other one. If, again, here's our hypothesis. And again, this is the one where I got that copy and paste problem. Should be, infinity there. Okay, there we go. If we got both positive terms for both sequences, we do the ratio of corresponding terms of the sequence a sub k over b sub k. Take the limit as k goes to infinity. If that's some real number L, so let's see, it actually has a L, and let's say bk diverges, which would be diverging to infinity, since it's adding up positive terms. Then what do we have here? We have, if we do the reciprocal of this thing, it's going to have the reciprocal limit. And by the definition of the limit of this sequence, the sequence of bk over a sub k, by the definition of the limit of a sequence for epsilon equal to 1, there exists a m greater than 0, such that if k is bigger than m, then this b sub k over a sub k is within that epsilon, which is 1, of that limit, which is 1 over L. So 1 over L plus 1 has to be bigger than this sum. Of course, this is a ratio, which is greater than 0. Multiply both sides by a sub k, and we have this relationship here. Now, solving for a sub k is greater than b sub k divided by this guy. All right, well, we got compound fractions, so I'll multiply top and bottom by L and get that in this form right here, L b sub k over L plus 1. Let's call that d sub k. Now we got our inequality going the right way. A sub k is bigger than d sub k. So that means that the sum of k equals 1 to infinity of a sub k is greater than or equal to the sum of k equals 1 to infinity of d sub k. But d sub k is L over L plus 1 times b sub k. Just factor the b sub k out of here. Well, the L over L plus 1 is a constant. Bring it out front here, which is a distributive property. And that sum goes to infinity. Infinity times this constant is still infinity. Oh, so wait a minute. But sum of a sub k is going to be bigger than that or equal to it. Well, it's infinity as well. So therefore, the sum from k equals 1 to infinity of a sub k diverges to infinity by the direct comparison test comparing to the sum from k equals 1 to infinity of this d sub k. Now, what if that limit is infinity? Well, by definition, there exists some m and n greater than 0, such that for k's greater than m, okay, the outputs a sub k over b sub k have to be bigger than n. Okay, and therefore a sub k is greater than b sub k times that n. We'll call that d sub k, and now our inequalities go the right way. The sum from k equals 1 to infinity of a sub k is greater than the sum of the d sub k. D sub k is n b sub k. Factor the n out front, and we get that. All right, so therefore, the sum from k equals 1 to infinity of a sub k diverges to infinity by the direct comparison test to d sub k, either one of these d sub k's, depending on which one it is. Well, that gives us our proof. So if we're in a situation where we think we have a geometric series or p series that should behave like the given series, but we can't get the inequalities work out so that we can use the direct comparison test, then we can usually use the limit comparison test. Sometimes, even when the inequalities do work out, it's easier just to apply the limit comparison test than it is to verify that the inequalities work out for the direct comparison test. So let's go back to our two examples and see if we can use the limit comparison test here. So as we said earlier, on this one we want to compare it to the to 1 over k cubed p series, which is convergent. So we suspect this thing's going to converge. We put the given series on sequence term on top, 1 over k cubed plus 1, the one we know, 1 over k cubed on the bottom. And then when we put this together, this is k cubed over k cubed plus 1, and we know that that limit is 1. One way to see it is multiply top and bottom of this by 1 over k cubed, and we get it in this form. That little piece right there is going to go to 0, so the whole thing goes to 1. So therefore, the sum from k equals 1 to infinity, 1 over k cubed plus 1, converges by the limit comparison test comparing to the convergent p series. So notice how you state your conclusion. The conclusion should say what series you're talking about, whether it converges or diverges, by what test, and in the case of a direct comparison or limit comparison, it's going to have to tell you what test, what series you're using to do that comparison with, or limit comparison. Here's another one. The sum k equals 1 to infinity of k over k squared plus k plus 3. As we said earlier, we want to compare to the harmonic series. So we take this term here, k over k squared plus k plus 3. That's the numerator. The denominator is 1 over k. Just invert and multiply. When you divide two things, two fractions, you get k squared here over k squared plus k plus 3. Hopefully you've done enough of these now to know that the leading terms are what matters, and that will have a limit of 1. So therefore, the sum from k equals 1 to infinity of k over k squared plus k plus 3 diverges by the limit comparison test, comparing to the divergent harmonic series, the sum from k equals 1 to infinity of 1 over k. So basically what's going on here with this limit comparison test is if you find a series, let's just do this last one. By this limit being 1, this says that both of these things are approaching 0 at about the same rate. Remember, the only hope a series has of converging is if the limit of the underlying terms goes to 0. Well, what we're doing by looking at this ratio, we're saying that they are both approaching 0 at about the same rate because we get a finite limit here. Okay, and so that's enough to make the overall conclusion be the same. Since they're approaching 0 at about the same rate, they're either both going to converge or both going to diverge. All right, on to the ratio test in our next video, but not before you study your textbook and do some homework problems over what we've talked about here.